Good day. So I am Carl Stephen Nicolyar from section 11B. So I'm here to discuss the three topics that we learned from prelim to final. So first is magnetosystem. So what is a magnetosystem? An aircraft magneto is an engine-driven electrical generator that uses permanent magnets and coils to produce high voltage to fire the aircraft's spark plugs. Aircraft magnetos are used in piston aircraft engines and known for their simplicity and reliability. It is often sold in pairs, not in singles, or a dual magneto. This compact device requires no external electrical source to operate. Two of the most common are the Slick Magneto by Champion Aerospace and the Bendix Magneto by Teledyne. So, these aircraft magnetos are well known across the industry and come from the trusted and reputable manufacturers. So, the mechanical system of the magneto includes the housing, the magneto drive shaft, and all non-electrical parts of the magneto. The housing is made of aluminum alloy because it will not interfere with the magnetic circuit. Aluminum is also due to its lightweight ratio and its mechanical strength and rigidity. Although the drive shaft is made from single hardened steel, it is mounted on a drive shaft that contains rotating magnets, cams, and gears to drive the fingers of the distributor. While it is also supported by a ball or needle bearing. There are two types of magneto housing designs. So first is the base mounted magnet which bolts to the motor accessory box bracket. The other is the flange mounted magnet. It is used on opposing motors, and the mounting flange is cast as integral part of the housing. The flange mounting holes are not also circular. The L-shaped locking piece holds the flange to the motor, which is convenient for slight magneto adjustment of motor time. So moving on to the next topic, which is spark plug components function and its operation. So first, what is a spark plug? A spark plug supplies the spark that ignites the fuel and air mixture, creating the explosion which makes your engine produce power. These small but simple plugs create an arc of electricity across two leads which are not touching but close enough together where the electricity can jump between them. So essentially, nothing more than a device to meter out electrical energy. Aircraft spark plugs look slightly different than most car spark plugs. The aircraft spark plugs, they have two electrodes, prongs, also known as prongs, on either side of a center electrode or central post. So the gap between the electrodes create the spark that ignites the fuel and air mixture. So now let's talk about the components of a spark plug. Components, first is the plug terminal. Plug terminal. The function of plug terminal is the portion that connected to the high tension cable coming from the distributor cap. It conducts the high voltage to the central electrode. Next is the ceramic insulator. Ceramic insulator is made up of aluminum oxide ceramic and acts as an insulator. It separates the central electrode from earth at up to 40,000 volts. It can be manufactured in plain form or with the profiles to prevent flashover. Next is the metal body. So metal body, it is a steel shell manufactured with precision rolled threads to secure fit and easy installation and removal. It provides electrical ground to the cylinder head and helps to cool plug by transferring the heat to the cylinder head. Fourth one, the central electrode, also known as central electrode. It is made of nickel-based alloys. It consists of a copper core enclosed in it, depending upon the type. The central electrode can be in platinum or iridium. The high voltage is applied to the central electrode from the secondary winding through the distributor. So, next is the ground electrode. Ground electrode, it is welded to the metal body of the SB. It makes spark with the central electrode. It is made of nickel-based alloys or iridium titanium reinforcement. Next is the sealing washer or gasket. It makes sealing with the cylinder head and help in heat dissipation. Simply, sealing washer or gasket, in the function is to seal the cylinder head. So, next is the insulator tip. Insulator tip is extended into the combustion chamber. It has greater influence on the thermal rating of the spark plug. And lastly, the electrode gap. Electrode gap, it is the distance in between the central electrode and ground electrode. The electrode has crucial role in the spark generation. If an appropriate gap is not provided to the plug, that if cannot produce sufficient spark to ignite the fuel and air, it may lead to misfire. As we say earlier, the two plugs there are two leads which are not touching, but close enough together that electricity can jump between them. So the gap between the two sparks, the two leads are called electrode gap. So that's all for spark plug components and function and operation. So moving on, turbine and ignition system. So next one, the turbine ignition system. So most aircraft engines rely on an electrical ignition system to create a spark, which in turn initiates or continues the engine combustion process. Many laypersons and technicians are familiar with the ignition system used on internal combustion engines for automobiles and general aviation aircraft. However, ignition system for gas turbine engines are probably the least understood and discussed of all ignition system. Compared to the automotive system, the spark discharge of a turbine ignition system is much larger. And in some cases, the spark over 100 times more powerful than the spark in an automobile engine. The function of gas turbine ignition system is to convert energy from some sources to a high-intensity electrical discharge. One good spark will initiate combustion of the fuel and air mixture in a turbine engine's combustor. However, several sparks are usually provided to ensure fast and reliable engine starts. Once the turbine engine is lit, the ignition system's job is finished unless the engine needs to be relit during an in-flight shutdown or until the next operational cycle of the aircraft turbine main engines, or also known as APU or Auxiliary Power Unit, begins again. So, the typical gas turbine ignition system consists of an exciter or exciters, an ignition lead or set of ignition leads, and an igniter plug or set of igniter plugs. Furthermore, the different types of ignition system can be broken down into two categories: the low tension ignition system and the high tension ignition system. So let's talk about the low tension ignition system and the higher tension ignition system. So first, let's talk about low tension ignition system. So lower overall ignition system causes higher reliability due to lower electrical stress, higher temperature capability, and lower part count. Smaller, lighter igniter and lead and exciter smaller terminations. Significantly fewer instances of dielectric flashover breakdown as compared to high tension system. So, low tension igniter, the igniter is almost impossible to quench because of the suppressed sparking, especially at elevated pressure of 5000 psi. It provides ignition capability for mission or safety critical applications. Improve wet spark capability over high tension igniter. High tension igniter easily quenched with fuel after short time in engine if fuel atomization nozzle issues exist. Also, low tension igniter is much smaller sizes and weight. It is typically 50% lighter than the comparable high tension igniter. So, low tension ignition leads do not require elastomeric seals or insulation, which will begin to degrade with exposure to temperatures above 450 degrees Fahrenheit or 232 degrees Celsius. Low tension leads provide overall higher temperature rating of the termination provider, provides higher reliability and no longer time between removal repairs. Champion low tension leads utilize ceramic insulators at both terminations and the high temperature conductors wire that can increase the terminal connection operating temperature up to 842 degrees Fahrenheit or 450 degrees Celsius, and lower incidence of termination dielectric failure. So basically, what I'm saying is the advantage of low tension to high tension. So next is the low tension exciter. As the low tension exciter designs have simpler output network, usually consisting of an output inductor to extend the spark duration. A low tension design reduces stress, which is high frequency oscillations associated with high tensions. On the high voltage switching element, unipolarity diodes and ground reference resistant circuit, thus improving reliability. Not as sensitive to high altitude operation due to the much lower operating voltages, no flashover potential in the terminal wells due to high voltage stress occurring from a quench igniter. Next is the disadvantages of the low tension. Disadvantages from igniter. Igniter design includes one more part and process due to the addition of a semiconductor pellet. Next is slightly higher cost of ownership igniter when comparing to its life cost and sparking life of high voltage system. Usually, due to much smaller igniter tips on low tension system. So, in the low tension lead and low tension exciter, there are no disadvantages. Moving on to the high voltage ignition system, a higher cost system due to use of elastomeric components and need to internally cool the ignition leads. The additional engine hardware required to support air-cooled ignition systems. A larger igniter lead exciter and connection termination weight increase is more significant due to cooling and the engine architecture to support cooling ignition system. So the advantages: one less part of the process in the igniter, is no semiconductor. Next is longer igniter life potential due to size difference, particularly when using iridium center and ground electrodes. Use of these materials significantly drive costs. Next is igniter. An igniter will quench at high pressure, preventing unnecessary continuous ignition at elevated pressure. The typical new part of quench pressure is 300 psi. Induced part quench pressure is less than 75 psi. This number will vary based on the exciter output voltage level. So, ignition spark can be directed in the combustor slightly further using recessed gap design, while the low voltage system is always a surface spark. So, what are the disadvantages of the higher voltage ignition system? So first, let's talk about igniter. So the disadvantages in igniter is it will increase weight size as a result of increased dielectric requirements. Increased dielectric strength requires longer terminations, greater insulator thickness, and larger internal flashover protection. All of the above lead to increased cost. Quenching of igniter at high pressure will cause unnecessary dielectric distressing of the igniter. Next is leak. So disadvantages are increased weight size and complexity as a result of increased dielectric requirement and ergot configurations. Next is more likely to have a dielectric and corona problem with components. Next, elastomeric components like seals, gasket, insulators, and wire jacketing have limited mechanical strength and can be easily damaged, allowing the potential for dielectric failure. And and lastly, the exciter. A major drawback to high tension system is increased EMI due to high ionization pulse. The higher voltage requirement and additional weight caused due to extra components needed to generate the high voltage. And lastly, sealing of the exciter enclosure becomes more critical in high voltage applications. So, that's all, sir. Thank you for listening, and thank you for this sem. Happy holidays and happy new year. God bless, sir. Thank you.